Welcome to our lecture. In this lecture we are going to discuss about photochemistry. My name is Dr. Zulfikar Ali Khan. So these are the contents of the lecture: Introduction to Photochemistry, Electromagnetic Radiations. We will discuss about photochemical reaction examples, basic laws of photochemistry, fluorescence and phosphorescence phenomena, and quantum yield in the end. So these are some important points about the photochemistry and photochemical reactions. Photochemistry is a branch of chemistry which is mainly concerned with rates and mechanism of reaction resulting from exposure of reactants to light radiation. Photochemical reaction affect the thermal reaction of the electronically excited state of the molecule, while the dark reaction of the molecule is the thermal reaction of the ground state. As we know, light energy is quantized. So what is photochemical reaction? A photochemical reaction is a chemical reaction triggered when light energy is absorbed by a substance molecule. This response leads the molecule to experience a temporary excited state, thus altering their physical and chemical properties from the substance initial molecule. There are various examples of photochemical reaction naturally. For example, photosynthesis in plants convert carbon dioxide and water into glucose and oxygen using solar energy. Development of the human vitamin D production by sunlight exposure. Bioluminescence, for example, an enzyme in the abdomen catalyzes a light producing reaction in the fireflies. So what are the primary photochemical process? Photolysis is the process by which a photochemical reaction is performed. The immediate consequence of light absorbed is a primary photochemical reaction. Secondary reaction are termed subsequent chemical shifts. So what are photochemical reaction? Photochemical reaction, a chemical reaction caused in the form of light by the absorption of heat. The consequence of the absorbing light of molecule is the development of transient excited states with chemical and physical properties that differ greatly from original molecule. What is photochemical dissociation? The photodissociation, photolysis or photodecomposition is a chemical reaction where photons break down a chemical compound. It is defined as one or more photons interacting with a single target molecule. There is no limited photodissociation to visible light. There are some basic laws of photochemistry which includes, we will discuss in this lecture. Photochemical equivalence law, fundamental principle related to light induced chemical reaction, which states that one molecule of the material respond to each quantity of radiation that is absorbed. So this is the electromagnetic waves regions, and we discuss here the wavelength. So this as we go from this these gamma rays, these are X-rays, they are very powerful. As we go from this side to this one, energy decreases. Then this comes ultraviolet region, and then ultraviolet region, it's this come visible region. Visible regions basically consist start from this violet, and then it ends at red. After the red lights, there is infrared region. So photochemical reactions, we irradiate light usually from 200 nanometer to 800 nanometer. So this light energy that we irradiate the substance. So the molecules in the ground state, they are, when absorbing the light, they are excited. Molecules then comes in the excited states at high energy, and then this excited state of the molecule is converted into product. So this is one natural example of the photochemical reaction, that is the photosynthesis, in which the plants use carbon dioxide and water in the presence of a photosensitizer like chlorophyll, and in the presence of sunlight it forms the glucose and oxygen is released. So mainly the region which is used for the to do the photochemical reaction is some ultraviolet region part and then visible region. So there is two type of reaction. One is photophysical. When light fall on a material, the molecule is electrons are excited, but after that if the molecule really emit the radiations and then it's come again into the ground state. This is photophysical phenomena. Another one is the photochemical, in which a material absorb light, it's form an activated complex, and then this activated complex is converted into product. This is photochemical reaction. So this is one of the famous example of the photochemical reaction is HCl cannon. So here it is a reaction take place by absorption of UV visible light is called a photochemical reaction. This is the simplest definition. The reaction which take place by absorption of heat, no light energy is required, is called thermal or dark reaction. So this is a famous HCl cannon experiment. In this when hydrogen gas and chlorine gas reacts in the dark, there is no reaction. But when we fill in this bottle hydrogen gas and chlorine gas and then we irradiate with the lamp, then and here we place a handball, and then after irradiation with the light there is this is converted into hydrochloric acid, and this is called HCl cannon. So this is the difference between photochemical reaction and thermal reaction. A photochemical reaction is a form of chemical reaction in which the reactant get energy as photons. Photons are the energy packets and their energy is quantized. So in the thermal reaction is a form of chemical reaction in which the reactant get energy as heat. So second point is photochemical reaction initiate when the reactants get energy from photons. Thermal reaction initiate when the reactants get heat energy. So third point is the presence of an appropriate light source is necessary for photochemical reaction. The thermal reactions may occur even in the absence of light or maybe in the presence of light. So this fourth point is the temperature of the reaction mixture has no direct effect on the initiation and progression of the reaction. In thermal reactions, temperature has a direct effect on thermal reaction. And last point is there is no need of a catalyst for almost all the photochemical reaction. The catalyst is normally the light energy. Most of the thermal reaction need a catalyst to accelerate the reaction. So thermal reaction may or may not need a catalyst to accelerate the reaction. So these are the basic laws of photochemistry. First law of photochemistry states the light must be absorbed for photochemistry to occur. This is the simplest concept, but it is the basis for performing photochemical experiment correctly. If light of a particular wavelength is not absorbed by a system, no photochemistry will occur, no matter how long one irradiates with the wavelength of light. Here when the light is fall on a reaction mixture, so only small amount of the light is absorbed. Most of the light is either it is transmitted, reflected, scattered or refracted. So for the first law which deals is the light must be absorbed. So for the photochemistry to occur. So this is a very simplest law. So second law is of photochemistry. This is also called Stark-Einstein law. States that for each photon of light absorbed by a chemical system, only one molecule is activated for a chemical reaction. So this law is true for the ordinary light intensities. So here if it is for 1 mole, it means that the light energy, 1 mole of light energy will activate or 1 mole of the reactant to convert into excited state. So this excited state of the molecule is then converted into product. So this is N stands for the moles, 1 mole of light energy. So this is a Jablonski diagram for absorption, fluorescence and phosphorescence. Basically, the broad term which we used is photoluminescence. Photoluminescence can be divided into two terms, fluorescence and phosphorescence, are routinely used to describe the emission of light from a sample. There are various definitions of fluorescence and phosphorescence are provided. For example, here this is one of the definition of the fluorescence. Fluorescence is which is from Wikipedia. Fluorescence is the emission of light by a substance that has absorbed the light or other electromagnetic radiation. So this is if you see, when this is the explanation, when light energy falls on a conjugated light absorbing material, this is the ground state of the, when it is for light energy falls, ground state of the material, electron is excited from the ground state to first excited state, which we show it S1. This is the second excited state for the electron, which we show it through S2. So this, between these energy level from ground state to first excited state, there are various vibrational and rotational energy levels. So when this electron, when light falls on the material, then we record here absorption spectra. When this electron is excited to the, suppose it comes here in the first excited state, so there is a lot of vibrational and then rotational energy levels. So this electron is then stabilized. It's called intermediate stabilization, and then there is interconversion, that this electron comes through this vibrational and rotational level, this comes here, and then this can comes over here because there is a lot of rotational and vibrational energy levels in between these states S0 and S1. So when this electron is then, when it emits the radiation, it comes in the ground state again. So this emission of the radiation, if it comes over here, if this or here, this, if this photon, this much energy, this is, or if it comes in the ground state from here to here, so it takes the interconversion takes 10 raised to the minus 13 second, and then this emission, when this electrons comes to ground state, then the emission of the photon, this is called emission spectra. So this is called the emission spectrum. It takes 10 raised to the minus 9 seconds to come in the ground state. So there are two ways. If it's electrons falls from here, this state to here, then this energy which emit is more. If it comes from this excited state to this one, then this energy which emit is less. So interconversion is non-radiative, it does not emit the radiation in the form of light. This is some kind of stabilization, intermediate stabilization. So this is a non-radiative emission of light, this is when interconversion, because there are a lot of vibrational and rotational energy levels between these excited states. So this is non-radiative, but this is when it falls from this state to this one, this is, it emits the radiation. So this is what we call emission spectrum. So if this electron, if it is excited electron, if it is comes here, if this is the, because basically change in the spin state, this is the singlet spin state of the electron, but if it is, this is called inter-system conversion. If you see this one, this inter-ISC, inter-system conversion. So this inter-system conversion, it's change the spin state from singlet, it comes in triplet state. From this triplet state, then it you can see here same thing, which is electron excited from the ground state, singlet state, it comes in the first excited state, and then this inter conversion, which is non-radiative, then it changes the spin state of the electron, is changed from singlet to triplet. This is called inter-system conversion, ISC, inter-system conversion. So this, then from here this triplet state, then it's come release the energy. This is called phosphorescence. It takes longer time to convert from singlet to triplet, and then when it relaxes this electron, this triplet state is slightly less in energy than this S1 state, so it is slightly lower in energy. So then this electron comes in the ground state by emitting the radiation. This phenomenon, when this triplet state it emits the radiation and comes in the ground state, this is called phosphorescence, and it takes some long time. It is raised to 10 raised to power minus 3 seconds to 10 seconds. So this is normally also called, this triplet state is also called sometimes forbidden, because of the if you see the orbital fillings rules, they, and other thing which is this non-radiation interconversion, they follows this Kasha's rule. So this intermediate stability which they achieved. So this is again the definitions of the fluorescence and phosphorescence. This is how we define the fluorescence, that is the decay of the S1 state back to the ground state is an allowed transition, since the both have the same spin multiplicity, that is singlet, resulting in prompt photoluminescence that occur in the picoseconds to nanosecond time scale and is called fluorescence. When it emits the radiation, this is first absorption. When the light energy fall on the material, this electron is excited from the ground state to excited state, and then this is when this inter conversion from this, if electron excited up to here, then there are a lot of vibrational and rotational energy levels steps, and then this is interconversion, and then this electron falls from here to this, again to this ground state, then it emits the radiation which is called fluorescence. So this is how we define the fluorescence, and then how we define this for phosphorescence. Since it is the photoluminescence that results from the triplet excited state to again to ground state, transition occur on a much slower time scale, microsecond to the thousandths of the second, and is called phosphorescence. So it takes a little bit longer time for the phosphorescence phenomenon to occur. So this is a practical example of photoluminescence, which deals with the absorption, fluorescence and phosphorescence for phenanthrene in the spectrum. So phenanthrene is an organic compound. When the light energy fall, this is the absorption spectra, which is started from, if you see, 200 to 300 nanometer. It's this, if you see this wavelength, then this is an absorption occur at high energy. If wavelength is shorter, the energy is high. So when this fluorescence occur, it is occur at less energy as compared to absorption. So this is the fluorescence spectra, you can see. And when this is phosphorescence occur, it is even lesser energy as compared to fluorescence and absorption. So this occur at started, if you see, round about 460 and at this 600 nanometer. So if you energy wise, if you see absorption, when the light falls on this phenanthrene absorption occur at higher energy, and fluorescence, which is the emission when the electrons of this phenanthrene comes from the excited state to ground state. Then this fluorescence occur, the emission, this you can see the photon which is emitted is of less energy as compared to the absorption. And then when this phosphorescence occur in this phenanthrene, this is even at less energy as compared to fluorescence and absorption. So this is the quantum yield. When we deal with the second law of photochemistry, this also gives us the quantum yield concept. The efficiency of the photochemical process is often expressed in terms of quantum yield, which we represent with this symbol psi. So it's the number of the molecules reactant in given time over number of the quantum of radiation absorbed in the same time. So energy absorbed per mole of the reactant substance is called 1 Einstein, or 1 mole of photon. You can say this is the 1 mole of the photon will excite 1 mole of the reacting substance. So mole of this N is the moles of the photons. So 1 mole of the photon we call it 1 Einstein. So quantum yield is ratio between the number of the moles of reactant consumed per Einstein. So this quantum yield is equal to number of moles of the reactants consumed divided by the number of Einstein of the radiations absorbed. So this is the primary and secondary reactions. The overall photochemical reaction may consist of primary reaction, immediate consequences of the absorption of light, and secondary reaction, subsequent chemical changes. So this is a ABC, a material. When light falls on this material, it's you can see it forms activated molecule, activated complex, which is also called photoexcitation. And this molecule after absorbing light can be converted into cation, and electron emits. This is called photoionization. It is also this material is dissociated into ions, positive and negative ions, and this material also can be dissociated into free radicals. Here you can see the free radicals. And sometimes this light energy can cause in this material intramolecular rearrangement or photoisomerization. So this is an example of if the quantum yield is high, what does it mean? So this is a quantum yield. When the quantum yield is high, greater than 1, it initiates the chain reaction and free radical reaction. So this is the primary process. When the light falls on this chlorine, it's converted into 2 chloride radicals, and then this chloride radical reacts with the hydrogen molecule to produce this HCl and hydrogen radical, and this hydrogen radical again react with chlorine molecule to form this HCl and chloride radical. This is the secondary process. So when quantum yield is less than 1, here you can see the physical deactivation is dominant. Here you can see in this reaction, when bromine irradiated, it formed the 2 bromide radical. This bromide radical reacts with hydrogen molecule to form this HBr, and hydrogen radical is produced. This hydrogen radical again reacts with bromine molecule to form the HBr and bromide radical. Here you can see this product, which is HBr, again reacts with hydrogen radical to form this reactant hydrogen, and bromide radical is produced. So these two, if you see, again this bromide radical and bromide radical combine to form this bromine molecule. So here this physical deactivation is dominant here when the yield is less than 1. But when the quantum yield is equal to 1, the product is produced in primary photochemical processes. So this is another example of photochemical reaction. This is the photochlorination of methyl group of the toluene. So this is the primary process. When light falls on this chlorine molecule, it produces the 2 chloride radical. This chloride radical then reacts with this toluene to produce this HCl and this monosubstituted chloride. One of the hydrogen is replaced with this chlorine atom. So this is another molecule of the chlorine. Again same primary process produces the chloride radical. Then this chloride radical reacts with this methylene, one of the hydrogen. So this hydrogen is eliminated as a radical to then this another chloride radical replaces this hydrogen to form this dichloro, and HCl is eliminated. This is third chlorine molecule. When irradiated, it produces two chloride radicals like here. This is, and then this chloride radical reacts with this. This is the third hydrogen is replaced with this chloride radical, and HCl is removed to produce this trichloromethyl benzene. So this is the how we use the half arrow to show this cleavage of this single covalent bond between the chlorine molecules. So when these two chlorine atoms, there is a single covalent bond. This is we show this is a homolytic cleavage with half arrow. One electron is shifted here and other electron is shifted here to produce this two chloride radical. And then this toluene is again this single covalent bond between this carbon and hydrogen is cleaved homolytically. So one electron is shifted here on this hydrogen and other electron is shifted on this carbon to produce this methylene radical here and this hydrogen radical. This methylene radical then combines with this chloride radical to produce this toluene molecule. So another chloride radical combined with this hydrogen radical to produce this HCl. So thank you very much for paying the attention. This is the end of the lecture.